I am Swiss, so I ended up with an Italian first name, a German middle name, and a French last name. My parents were politically correct before that was even invented. Carlo Heinrich Sequin. I grew up in Basel on the River Rhine, and I attended the Mathematik-Naturwissenschaftliche Gymnasium, which is a high school that focuses on math and science. And then during my university years, I heard my math lectures in this 500-year-old institute, where many famous mathematicians have lectured, such as Leonhard Euler, inventor of the imaginary numbers, or Jacob Bernoulli, the inventor of the logarithmic spiral. So from an early age on, I was fascinated with numbers and geometry. And then in the 11th grade, we had a really cool subject called descriptive geometry. That's where we constructed the intersection of cones and cylinders by just using compasses and rulers, no computers. And I thought that was really cool stuff. So in many of my future jobs, I was then focusing on the geometry component. And for instance, laying out an integrated circuit is one huge geometry problem. On the left is the first solid-state TV camera based on charge-coupled devices that we built at Bell Labs. In the middle, you can see the reduced instruction set microcomputer chip that I developed with my colleague Dave Patterson and our students at UC Berkeley. And then a little later, computer science needed a new building, and my geometry went from 2 dimensions to 3 dimensions. More recently, I created programs that help artists to do geometrical sculptures, such as the Pax Mundi sculpture on the left. But today I will talk about mathematical visualization models. And you see 2 rapid prototyping models that I recently made. Why is geometry so useful in so many different fields? It's a power tool for seeing patterns. And discovering patterns is really the basis for true understanding. For my sculptures, for instance, I find such patterns in inspirational artwork by more intuitive artists, and then I capture them in the form of a computer program. But seeing patterns is really something that happens in your mind. So in this talk, I will introduce you to ways of seeing things in your mind that cannot be seen in just an ordinary way. The left figure may look like 6 triangles or maybe a hexagon with some internal lines. But if you rotate this figure in 3 dimensions just a little bit, it suddenly starts to look like a 3D cube. This is a simple example of an image that is composed in your mind. And here is how our high school teacher introduced us to seeing mathematical objects. We start with a very big point, and I'm sure everybody can see it. But now there's a somewhat smaller point. Can you still see it? Come on, are you blind? Say yes. Oh, good, good. Phew. Much smaller point. Now, who can still see that? Raise your hand. Oh, good eyesight. All right, much smaller point, tiny point. Who can still see that one? Amazing. And now a mathematical point. Now, who can see that? Those are the true mathematicians, okay? Because it's in your mind. You know where that point is, and it's infinitely small, but you have no trouble seeing it. Now we use the same kind of mathematical seeing to go from a single point to a 4-dimensional hypercube by a process called extrusion. And for that, I will have to put on my magical gloves. Now, I start out with just a mathematical point. And you know it's infinitely small, but you know where it is. It is right here. Can you see it? All right. Now, because I have these magical extrusion gloves, I can grab this point here, and I can stretch it into a line. Okay? Can everybody see that mathematical line? I hope so. Now, I try to hold this line with just one hand, and here it is. Okay? And now, again, I grab that line from the top, and I do my magical extrusion into a square. Everybody see that square? I hold it by a corner here. Okay. I can lay it flat onto my hand. Now again, I take my magical extrusion glove, I touch it from above, and I pull the whole square up like that. And what do I get? A cube. You're right. So here's the cube. You can see it. I can rotate here in 3 space. Now comes the really difficult step. I want to now take this cube and extrude the whole cube into the 4th dimension. Okay, and that's a little difficult. Okay, and maybe you can understand why this is difficult by an analogy by looking at flat land. Let's assume for the moment there's a plane, and in that plane there are these two-dimensional worms, and they're bound to the plane. They can only move in the plane. They cannot cross each other or any objects. However, they're mathematically smart, and they know about regular polygons, even though they cannot see them the way you can see them, because they can only walk around them, measure their length of the sides, measure the various angles, make sure that all of them are the same, and then they understand what a regular polygon is, and now they can see it in their minds. But one day, a visitor comes from the 3D world and tries to explain to them what a cube is. She says, you know, just take that square and move it upwards. No, not diagonally, really upwards. And upwards means a direction that is perpendicular to both of the edges of your square. And those flat worms, you know, they scratch their heads and they have a hard time of really doing that. But, you know, the smarter ones, they get it. Says, yeah, I can see it must be out there somewhere. Okay? So they have the same difficulties that we have when we try to see the extra dimension for the hypercube. And perhaps out there are some four-dimensional aliens, and they're looking down on us, and they smile at our efforts of trying to point into the fourth dimension. Say, no, that's not it. That's just diagonal in 3 dimension. But anyhow, the fourth dimension is out there. Let's go back and look at some more beautiful geometry that we can actually see it, the Platonic solids. Those 5 Platonic solids, the tetrahedron, the octahedron, the cube, the icosahedron, and the dodecahedron, have been known to mankind for more than 2 millennia. They're all totally regular polyhedra, and that means that all their faces are indistinguishable. They're all the same, all the edges are the same, and all the vertices are the same. Now, the surfaces of these objects are composed of 2-dimensional regular polygons. But in 2 dimensions, there are infinitely many of these 2-dimensional regular polygons. They go from triangles to quadrilaterals to pentagons, all the way up to infinitygons. Okay? But in 3 dimensions, there are only the 5 regular polyhedra that you see here. Now, who knows why? Who could prove that to their colleagues or maybe to their grandmother? In order to construct the surface of a Platonic solid, which is made from these 2D polygons, so that they form real physical 3D corners, you have to use at least 3 of those polygons. And then with 3 of these polygons, we can make some kind of a corner. Okay? So if we start, for instance, with just 3 squares, we can fit 3 around a joint vertex. And now we forcefully try to close this open gap. And we cannot do it in 2 dimensions. But if we allow to go in a 3rd dimension, yeah, we pop out this 3-dimensional corner. And that's a regular cube corner. And 8 of those corners make up a cube. We could also do that with starting with 3 pentagons around the joint vertex. And then we would get the dodecahedron shown at the bottom. Now we can see why there are exactly 5 Platonic solids. When we use triangles for our surface facets, we have a choice. We can either use 3 triangles forming a 3-sided pyramid, or we can 4 around the corner, or 5 around the corner. If you use 6 triangles around the corner, it gives you a flat kind of kitchen floor, okay? No longer a polygon. So we have 3 options for triangles. But when we use squares, only 3 squares work. By the time we add a 4th square, again, we have flat tiling. And with pentagons, 3 pentagons work and form the dodecahedron. Any higher n-gons are useless. You know, hexagons just make a flat tiling, and if you take heptagons or higher, then they don't even fit around the corner anymore. Okay, if you got that, then here is the test. Now we take a leap into the 4th dimension. We apply exactly the same kind of thinking to answer questions. How many regular Platonic polytopes are there in 4D? So how can we find out? Well, the key insight is that we need to use these regular Platonic solids to essentially make the surface or some kind of a thick crust of these 4-dimensional objects. Okay. And now we have to see how we can form 4D corners out of these 3-dimensional Platonic solids. We took a few regular n-gons that did not quite fill the space around the vertex, and then we forced this gap to close. Now we do this one dimension higher. We'll take a few Platonic solids, and I'm using the same models, but now assume that this is just a front, and that basically I'm holding 3 cubes in my hand. So behind each square, there's a complete 3D cube, okay? And they all share this one edge here pointing towards you. And now I'm going to force this empty wedge of space out of existence by closing that gap. But now I cannot do that in 3 dimensions, obviously. But when I do this, and I allow it to go into the 4 dimensions, something magic happens. I get a 4-dimensional corner. Now we just have to count for how many different ways we can do that, given the Platonic solids, the 5 ones that we have. In this case now, the crucial value is the dihedral angle. That is the angle between 2 adjacent faces. For the cube, it would be 90 degrees. And this dihedral angle tells us how many of these objects we can fit around a common edge, and then how much empty space is left over that we can now force to close so we pop out into the 4th dimension. For a tetrahedron, that critical angle is about 70 degrees. So we can either fit 3 or 4 or 5 tetrahedra, because the sum is still less than 360 degrees around an edge. And here's now the complete analysis. You know, with 3 tetrahedra around an edge, we get something called a simplex. 4 make the cross polytopes, 5 make the 600 cell. We have seen we take 3 cubes, that gives us the hypercube. Using 3 octahedra gives something called a 24 cell, and then using 3 dodecahedra gives a 120 cell. Now the icosahedra is kind of useless. Why? Its dihedral angle is 138, okay? Times 3 is more than 360. It's sort of like the heptagon, it's too much. You cannot fit 3 of them around a particular edge. Okay? All right, you say, well, that's nice in the abstract, but can we get the feeling of how these things actually may look like? Now, unfortunately, we can not look directly into 4-dimensional space, but we can make projections. We can project these things from 4-dimensional space down to 3-dimensional space. And then in our mind, we can maybe understand what's going on. Now, how do we do this projection? We could cast shadows. On the left, you see a shadow of a cube. It's a pretty formless, featureless blob, you know, not much of a cube in there. So it's much better to only take the edges of these objects and make a wireframe and then project that one down 1 dimension. On the right-hand side, I think you can see that as a cube, okay? You can form that image in your mind, even though the figure is only 2-dimensional. And that's exactly what we're going to do. We're essentially going to take a 4-dimensional object. I showed you the extrusion of this hypercube, okay? And we project that object from 4 dimension down to 3 dimension, and that's my 3-dimensional projected result. And now in your mind, you can get an idea of what this 4-dimensional object might look like. Actually, we have different possibilities of doing projections. Just as in engineering, we can either do oblique projections, as this one here, or we can do perspective projections. Here's a perspective projection of a hypercube, okay? We can even use some color, and here, for instance, I use red to indicate sort of like the front object, and then blue is the extruded back object, and then green are the lines that go in between connecting front to back. Now let's start the parade of the 6 4-dimensional regular polytopes. We start with the 5-dimensional simplex. It's composed out of 5 tetrahedra. Now in 4D, all 4 corners are at equal distance from each other, and that means all the edges are of the same length. They look different here because I used a perspective projection. If you use 4 tetrahedra around the shared edge, we get a 16 cell. It's also called the cross polytope. It has a total of 16 tetrahedral cells, but only 8 vertices. And it is the geometrical dual of the hypercube or tesseract, which has 8 cubic cells and 16 vertices. Here I used a perspective projection with depth color information. My favorite is the 24 octahedron that make up the 24 cell. It is self-dual. This means it has the same numbers of cells and vertices, and it has 1152 symmetries, but unfortunately, you can only see them in 4 dimensions. Finally, here are the two big ones. Here's the 120 cell made of 120 dodecahedra. It has 1,200 edges. But in this parallel projection, you can only see about half of them because some edges obscure some of the other ones. In this perspective projection, you could actually see, in principle, all the 1,200 edges. But some of them are very close to the center, and they get very, very small. And finally, last but not least, here is the parallel projection of the 600 cell containing 600 tetrahedra. And this is a model made out of drinking straws by David Richter. Now, this constructive process can be continued. We can now use these four-dimensional regular polytopes, all 6 of them, and try to make 5-dimensional corners for making the 5-dimensional polytopes. Doing the same kind of analysis as we have done before, we can show that there are only 3 regular polytopes in all the dimensions above 4 dimensions. And here, I'm showing you the projections of the 3 regular 6-dimensional objects: the 6-dimensional simplex, the 6-dimensional hypercube, and the 6-dimensional cross polytope. But rather than giving you the proof, let me use the last 3 minutes to really introduce you to some other strange and beautiful objects. Let me give you a glimpse of the added capabilities we obtain when we go to higher dimensions. In 2 dimensions, a strip of material can bend and curve, but it can never cross itself. And no matter how badly we distort it, it can never flip over. So the same green side is always pointing upwards. But in 3D space, we can do more interesting things with a strip of paper. We can either close it straight into a cylindrical shape or into an annulus, or we can twist it through 180 degrees so that the colorful front side matches up with the black and white back side. And now we get a single-sided surface. Both sides are connected, and you can go from one to the other without having to step over the edge. This is a Mobius band. It is a fascinating shape. I encourage you, take a strip of paper and some Scotch tape and glue the ends together in this twisted manner, and then cut it down the middle along the black and white line. What do you think you will get? You have to try that yourself. This Mobius band also forms a crucial element in many intriguing geometrical sculptures. Aurora Borealis is just one long wound-up Mobius band, but the tripartite unity by Max Bill is of genus 3, and that means it's made of 3 Mobius bands. The minimal trefoil is a composite of 4 Mobius bands, and the heptoroid, which I did with Brent Collins, is a really complicated structure made of 22 Mobius bands. All of these structures have just one single continuous edge. Okay? And we could do more complicated stuff by having more of these edges. But the big question is, can we have a single-sided surface that has no edges whatsoever? Something like a sphere or like a donut. But both of these shapes are two-sided. They have a visible outside of some color, and maybe on the inside they have a different color. Can we do a single-sided surface like that? The answer is yes. On the left, you can see the 2 simplest examples, Boy's surface and the Klein bottle. And then on the right is something I cobbled up by gluing together the edges of 8 separate Mobius strips. The one in the middle is probably the one that some of you are familiar with. It's the most familiar kind of single-sided surface without edges, and it comes in many different shapes. On the left is Cliff Stoll from Berkeley, presenting one of his large classical Klein bottles. But all the shapes on the right are also Klein bottles, where the inside is always smoothly connected to the outside. Here is yet another example. That's also a Klein bottle. Some of these make nice sculptures, and some of them, I guess, would even make nice climbing structures. The last cool fact I want you to know is every Klein bottle can be cut in exactly 2 Mobius bands. Here I show you how you can do this for the classical shape of a Klein bottle. And here is a more twisted version of such a Klein bottle, and when I cut this one apart, I actually get 2 Mobius bands that are interlinked. But these intriguing shapes are really the topic for another talk at some other time. In conclusion, geometry is a powerful tool for almost all subsets of science and engineering, but it also offers much beauty and fun. And the latter is really important to me because I believe that the secret of a happy life is to find out what you really like to do and then find somebody to pay you to do it. And I have been in that state for the last 30 years of my life, and I very much hope that you will be able to do that too. Thank you for your attention.